Hello everybody, we're ready to start our final chapter, chapter 5, dealing with, in section 5.1, the concept of sequences. Now this is something you've actually studied before, I'm sure, because it's a significant part of a pre-calculus course. But we do need to review this material, make sure we understand notation and basic tools that we use to understand sequences before we can do anything from a calculus perspective with them. So the first thing we're going to do is we're going to start with a definition of a sequence. And a sequence is simply an ordered list of numbers. And the key word in there is ordered. Okay, the list must be ordered. So that means there's a first term in the sequence, there's a second term in the sequence, a third term, and so on, up to perhaps an nth term. And if we stopped there, this would be what's called a finite sequence. It doesn't have to be finite sequence, though it could go on forever, which we would indicate with an ellipsis here, that this runs on forever and ever. Okay, so again, the numbers in the sequence are called the terms of the sequence. And this little subscript, the subscript 1, the subscript 2, the subscript 3, this is the index for this terms. Okay. Now the notation we can use for this, instead of always writing out the terms in an ordered list as we're doing here, we could also write this with the curly braces. When we see the curly braces around an a sub n, and sometimes we'll write this n starts at 1 and goes to infinity, or sometimes we'll leave that off and we'll just write the a sub n. But this is another notation for a sequence as well. It's the same sequence as up here. Now we can think of this sequence actually as being a function. So a sequence can be determined, or you may say defined, by a function. Sometimes we'll call that the generating function for the terms of the sequence. And so as the inputs to this function, we'll use the counting numbers. So the index values 1, 2, 3, and so on. And so we may describe a sequence by giving you the curly braces and then the rule or the function within the curly braces. So 2 raised to the nth power is the function that determines this sequence. And that means if you were to write out the terms, when n is 1, you'd get 2 to the 1. When n is 2, you'd get 2 squared. When n is 3, you'd get 2 cubed, and so on and so on. Okay? Now, sometimes, excuse me, sometimes we may define our sequence recursively. What that means is we'll give you a first term to the sequence. Maybe we'll give you, say, a sub 1 is 2. And then we'll give you a rule for how the next term of the sequence is generated from the previous term. So we'll give you a rule like a sub n is, say, 5 times a sub n minus 1. And so this is called the recurrence relation. And along with this sort of initial condition or starting value, the recurrence relation will define the sequence. So obviously a sub 1 is 2, that's your first value. The next value, you look at the rule. The rule says to find the next value, you take the previous value and you multiply it by 5. So 5 times the 2 gives you the next value. then the rule says to find the next value, you take the previous value to it and multiply by 5. So 10 times 5 gives you 50. To find the next term, you take the previous term, multiply by 5. So 50 times 5, 250. And there's the pattern that generates this sequence. Okay? Now, you can look at a recursively defined sequence like this, and you can figure out the function. Find the function that generates this sequence. Well, a sub n. First term is 2, second term is 10, third term is 50, fourth term is 250. A simple rule for this would simply be 2 times 5 to the n minus 1 power. And the way I figured that out was I looked at the rule here and I say, oh, I'm multiplying by 5 on the previous term to get the next term, so I'm going to get 5 times 5 times 5 times 5 repeatedly. That's 5 to a power. So I just had to figure out what power works with that. And of course, the starting value of 2 meant I had to multiply by 2 for this. So there's a function form for this recursively defined sequence. In general, the function form is more useful. Than the recursively defined form. The recursively defined form has a nice theoretical feel to it. We can describe things easily based on a recursive relation between the terms sometimes, but to actually work with the terms, the function generating the sequence is much easier to work with. All right, now let's take a look at a few examples just to make sure we understand what we've said so far, and then we'll move on to the next concepts here. Let's take a look at problem number 6 from the exercises. You're simply asked to find the first 6 terms of the sequence. So I'm sorry, that's for the first few. For number 6, find a formula for the nth term of this arithmetic sequence, whose first term is a sub 1. So a sub 1 is 1. And the relation we have here is a sub n minus 1 minus a sub n is 17. All right, so that's what they tell us is the relationship between the terms. So this is like a recursively defined function here, isn't it? What I can do is I can solve this. I can say, let's solve for a sub n. Bring the a sub n over, bring the 17 over to the left. You get that a sub n by itself, brought over, is a sub n minus 1 minus 17. So if a sub 1 is 1, the way I'm going to get the next term, a sub 2, is it's a sub 1 minus 17. I'll get a minus 16. To get a sub 3, I'm going to take that minus 16 minus a 17, get a minus 33, and so on. Okay, so that's how the terms are getting generated for this sequence. So now, what would that look like in terms of a rule? Well, to find it as a function, think about it this way. You're repeatedly subtracting 17, aren't you? So subtract 17 n number of times is part of this rule. Then figure out what you would have to add to that to make this work. Well, let's see. To make a sub 1 1, negative 17 times 1 is a negative 17. I'd have to add 18 to that. And that works now, right? A sub 1, negative 17 times 1 plus 18 is 1. A sub 2, negative 17 times 2 is a negative 34, plus 18 is negative 16, and so on. So this is the generating function for that sequence in problem 6. All right, let's try a second example here. Take a look at problem number 8. In 8, find a formula for the nth term of the geometric sequence, whose first term is 1. And the relation here is that a sub n plus 1, when divided by a sub n, is 10. Well, that simply means if you multiply both sides by a sub n, that the next term in the sequence is 10 times the previous term in the sequence. So that means that a sub 2 is going to be 10 times a sub 1. 10 times 1, 10. A sub 3, this would be 10 times a sub 2. 10 times a sub 2, 10 times 10 is 100. And so on. A sub 4, 10 times 100, 1,000. So you're looking for the function that generates these terms. Well, a sub n is equal to 10 raised to what power would do that? Well, when you want n is 1, you want 1. You want this to be the 0 power. So take that as n minus 1 as the power. Let's see, when that's 2, 2 minus 1 is 1, 10 to the 1 is 10. When the subscript is 3, 3 minus 1 is 2, 10 squared is 100. It works fine. This is a generating function for that sequence. Okay, let's take a look at number 10. In number 10, you have to find an explicit formula for the nth term of the sequence. In other words, for the generating function of the sequence, where the terms are given to you. At least that many are given. And so what I recognize here, and the little hint the author gives you, is if you were to add 1 to all of these, you'd get 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, which you may recognize as the squares of whole numbers. In other words, this here, this is simply 1 squared minus 1. This is 2 squared minus 1. This is 3 squared minus 1. That's 4 squared minus 1. So the generating function, or the nth term, is simply n squared minus 1. And there you have it. Okay. All right, let's take a look at number 16. Find a function that identifies the nth term for this recursively defined sequence that you're given. In 16, the recursively defined sequence we're given is that a sub 1 is 1, and a sub n plus 1 is equal to n plus 1 times a sub n. In other words, a sub 2 is going to be 2 times a sub 1, or 2. A sub 3 is going to be 3 times a sub 2, or 3 times 2, which is 6. A sub 4, 4 times 3, times a sub 3, so 4 times 6 is 24, and so on. And this is simply the pattern for the exponent, or for the factorial function. So there's your generating function for this. Okay. All right. Let's take a look at why it is we care about having this generating function form as opposed to this recursively defined form. Okay? And the reason we want a function form for a sub n as opposed to the recursive definition is because the function form allows us to analyze the sequence using limits. And after all, limits are what calculus is about. And this is how we do the analysis. We give you a definition. Definition. If, when we take the limit as n goes to infinity of this generating function, or of this form of a sequence, and we get a value called L that exists, then we say that this sequence converges to that value. if the limit of the function that generates the sequence exists as a finite value, we'll call L for limit, then the sequence converges to that limit value. Okay, and that's the definition of what it means for a sequence to converge. Okay, if this limit does not exist, if that limit does not exist, then we say that the sequence diverges or is divergent. Two ways of saying the same thing. Okay? This is the reason that we want to use the functional form as opposed to the recursive form to define our sequences. It allows us to use the limit process to define this concept that we're really very interested in for any sequence, and that is whether the sequence converges or diverges. Okay? Now, just a little reminder about the limit laws. So, if you're given that the sequence a sub n converges to A, and the sequence B sub n converges to the value of B. That means the limit of A sub n is A, and the limit of B sub n is B as n goes to infinity. And constant value called C. Then you know the following. The limit as n goes to infinity of that constant value is that constant value C. You know that the limit as n goes to infinity of C times A sub n is C times the limit of A sub n, and the limit of A sub n is A, so C times A. You know that the limit as n goes to infinity of the A sub n sequence plus or minus the B sub n sequence is the limit of the first one plus or minus the limit of the second one, and therefore A plus or minus the B value. You also know that if you take the product an times bn, that's the limit of the A sub n, which is A, times the limit of the B sub n, which is the B. And finally, if you take a quotient, you're taking A sub n over B sub n. The limit of A sub n is A, the limit of B sub n is B. You're going to get A over B, provided that the limit value B is not 0, and also provided each one of these terms, B sub n, is not equal to 0. Okay. All right. So let's take a look at applying these limit laws, perhaps, or just trying to compute some limits in general. We'll take a look at problem number 24. In 24, we're given that the limit of A sub n is 1, the limit of B sub n is negative 1, and the negative of B sub n is less than A sub n. Okay, so in other words, the absolute value of the B sub n terms is smaller than the A sub n values. That's another way to say that. For all n. Okay. Then in 24, what is the limit as n goes to infinity of 1/2 B sub n minus 1/2 A sub n? Well, all you have to do here is say it's the limit of this minus the limit of this and factor out the halves. So that's 1/2 times the limit of B sub n minus 1/2 the limit of A sub n. The limit of B sub n is negative 1. The limit of A sub n is 1. And so you get a negative a half minus a half, or negative 1 is your answer. Okay. All right, how about problem number 28? We want to find the limit as n goes to infinity of the expression n minus 1 squared over n plus 1 squared. Now, one way to do this would be to simply realize as n goes to infinity, n is the dominant term, the minus 1 is inconsequential, the plus 1 is inconsequential, and simply say this is the same as n squared over n squared, which is 1, and the limit of 1 is 1. Okay. Now, another way to do this would be to say as n goes to infinity, this becomes infinity squared, the bottom becomes infinity squared, or infinity, and therefore you're getting this indeterminate form, infinity over infinity, which implies we can use L'Hopital's rule. And by L'Hopital's rule, you take the derivative of the top versus the derivative of the bottom, and you compare these now. And again, it's infinity over infinity. So you apply L'Hopital's rule again. The derivative of the top, the derivative of the bottom, 2 over 2 is 1, and the limit of 1 is 1. It's easier if you just throw away the non-dominant terms in this case, since your limit is going to infinity. All right, let's take a look at number 30. The limit as n goes to infinity of n to the 1 over n power. Now, if you think about it, as n goes to infinity, the base is infinity, and this is 1 over infinity is 0. You're getting infinity to the 0 power form, which is an indeterminate form, which we talked about in Calc 1, and you can use L'Hopital's rule on something like this as well. Now, the trick to doing this is the following. You say, let's give this limit a name. Call it y. Now, I want to get this 1 over n out of the power, and the tool that does that for me is the natural log, or any log, but I'll use the natural log. Take the natural log of both sides. Since the natural logarithm is a continuous function, you can pass that within the limit. And therefore you're taking the limit of the natural log of n to the 1 over n. And now that you're doing this, this 1 over n can come down in front. And here, that's where you're getting the natural log of infinity, which is infinity, 1 over infinity in the denominator like that, gives you infinity over infinity form, and you want to apply L'Hopital's rule to this. Okay, the derivative of the natural log of n in the top is 1 over n. The derivative of 1 over n in the bottom is negative 1 over n squared. Derivative of n in the bottom is 1, and so you get 1 over n over 1, which goes to 0. And so what we learned here is that the natural log of y is 0. Now, our goal was to know what y was, right? Y was the limit we wanted. So if the natural log of y is 0, y is e to the 0, which is 1. And that's our limit in this case, 1. There's your final answer to the problem. All right. So, you're getting the idea. The reason we want to express our sequences as functions is so we can use this tool of the limit to evaluate the sequence in terms of whether it converges or not. But we have to face a reality about limits. Sometimes limits are very difficult to compute. Okay? We can't always compute limits. That's a problem. Okay? So, to that end, we have a couple of tools to consider. Okay, sort of workarounds for the cases when we cannot compute the limits of our sequence terms. The first one is called the Squeeze Theorem. Some people refer to this as the sandwich theorem, so he knows it's two names. It's the same theorem. Okay? And the Squeeze Theorem simply says this: if you've got three sequences, you've got a sequence a sub n that's less than or equal to the terms b sub n, which is less than or equal to the terms of the sequence c sub n. Okay? And if the limit of a sub n is the same as the limit of c sub n, meaning the limit of the smallest of this chain of inequalities and the limit of the largest, if those are the same, if they have the same limit, then this sequence that's squeezed between them must also have the same limit. And so the idea here is, if you've got some complicated limit to compute, some term b sub n that's very difficult to work with, if you can find a simplification to make it a bigger term and a simplification that makes it a smaller term, such that both of those happen to go to the same limit, then you don't have to work with this complicated expression. It's squeezed between these two, going to the same limit value. Okay? Now, the thing about this is the theorem doesn't, or in this case, the theorem will tell you what the limit is for this sequence. It's trapped. That is the limit. That is the sequence converging to L. Okay? But there are other more general forms where we can't even get that much information about a sequence. Okay? And so sometimes we have to satisfy ourselves with only knowing whether a sequence converges or not. Without actually figuring out what the sequence converges to. In other words, in any case where you can compute the limit, as in all our previous examples and our definitions, then you've computed what the sequence converges to. But sometimes we can't even do that. We can just determine that the sequence converges, but we won't know what it converges to. And the tool that does that for us is what's going to be called the Monotone Convergence theorem. Now, to use that theorem, we have to define a couple of terms first. So, definition. We say that a sequence is bounded above if there is a value called capital M such that a sub n is always less than or equal to that capital M value. Okay, so that's what bounded above means. We say that the sequence is bounded below if there is a value I'll call little m such that little m is always smaller than the a sub n terms. Okay? Now, if a sequence is both bounded above and bounded below, then we just say it's a bounded sequence. Okay. Second definition. Consider bounded to be a first definition. Second definition is concerning a sequence that's increasing or decreasing. There we go. We say that a sequence A sub n is increasing if the n plus 1 term is always bigger than the n term. We say it's decreasing if the n plus 1 term is less than or equal to the n term. Okay. And note that A sub n is called monotone if it is either always increasing or always decreasing. Okay. Now, why do we care about this idea of a sequence being bounded? Why do we care about the sequence being increasing or decreasing? Is because when we put these two things together, we get what's called the Monotone Convergence theorem. Okay. If your sequence is bounded and monotone for an n value bigger than or equal to some fixed value. This fixed value can be anything. 1, 10, a trillion, it doesn't matter. If all of the terms eventually are bounded and monotone, then that sequence converges. So let's look at a couple of examples of how we might deal with this. Problem number 32. State whether the sequence is bounded and whether it's eventually monotone, increasing or decreasing. So the terms we have here, the A sub n is the natural log of 1 plus 1 over n. Okay? So is this bounded? Well, let's think about what the largest this could ever be, could possibly be. Okay? When n is 1, you get 1 plus 1 over 1. 1 plus 1 is 2. You get the natural log of 2. As n increases, 3, 4, 5, this number in here gets smaller than 2. So you're taking the log of smaller and smaller and smaller numbers successively. So this is bounded above by the natural log of 2. Okay. What about bounded below? As n gets infinitely large, this becomes 1 over infinity, which is 0. You're just approaching the natural log of 1 in value. So you're bounded below by the natural log of 1, which is, of course, 0. Okay? Now, is this monotone? Well, let's take a look. Think about the terms natural log of 1 plus 1 over n in comparison to the natural log of 1 plus 1 over n plus 1, which would be the next term in the sequence. Is there a general form to this that convinces you that one of them is always larger than the other? Well, sure. This is going to be bigger than this because this denominator is larger, making this fraction smaller, making this argument of the log smaller than this one. Another way to say that would be to simply say, let's go ahead and exponentiate this to get rid of the natural log. And look at this. Is it true that this term is smaller than this term? Well, yeah. Subtract 1 from both sides to get rid of that. Is it true that this is the relation? Of course. How do we know that? Well, if you simply flip both sides of the inequality, 1 over n flips to n. When you flip the sides, you have to flip the inequality. 1 over n plus 1 flips to n plus 1. And it's pretty easy to see that n plus 1 is bigger than n, right? So you've proven that this inequality holds for all values of n that are under consideration here. All right, let's take a look at problem number 34. I think we can actually slip that in on the previous sheet of paper. Cosine of n squared. And the question again, is this bounded? Is it monotone, increasing or decreasing? Well, certainly the cosine function is bounded. You know that the cosine wave is trapped between a height of 1 and a height of negative 1. So this is bounded between negative 1 and 1, for sure. Okay? Is it monotone? Certainly not. It oscillates, right? Not monotone. This oscillates. So it's not a monotone function. We could not possibly apply the monotone convergence theorem to it. Okay? All right, let's take a look at number 36. In 36, we have the function generating our sequence n to the negative 1 over n for n bigger than or equal to 3. Okay? And so the question is, right, is this bounded? Is it monotone? Okay. How would we determine if this thing is bounded? Well, I'm going to suggest it's bounded above by 1. And let's see if we can prove that. N to the negative 1 over n. I want to prove that's greater than or equal to 1 for n bigger than or equal to 3. Now this here is simply another way of saying 1 over the nth root of n. Now if I want to prove that 1 over the nth root of n is less than or equal to 1, isn't that the same as if I flip this, proving that the nth root of n is bigger than or equal to 1? So how would I do that? Well, take both sides to the nth power. N is what you're left with on the left side. 1 to the n is 1 on the right side. And since n is bigger than or equal to 3, n is certainly bigger than or equal to 1. Okay, so you've proven this thing is bounded below by, or bounded above by, by 1. Okay? It's bounded below by this first value. How do I know that? Well, I first can tell you that this function is always increasing. And if I could prove to you that this is a function that's always increasing, then certainly its smallest value is its first index, right? Because the second index, third index have to be bigger than the previous ones. And so your bound from below will be the first index value plugged in, okay? Which is 3. Okay? Now, how do I prove to you that this is an increasing function? Well, a good tool to determine if a function is increasing or decreasing, since this is calculus class, is the derivative, right? So I'd like to take the derivative of n to the negative 1 over n. Now, that's a function that's difficult to take the derivative of unless I use a log to help me. So again, find y prime is my goal. Take the natural log of both sides. Use the rule property of a natural log to bring the power down. And now take the derivative. The derivative of the natural log of y is the chain rule. The derivative on the right-hand side is going to be the product rule. The derivative of negative 1 over n is 1 over n squared. And the derivative of the natural log of 1 over n is, natural log of n is 1 over n. So you get negative 1 over n times 1 over n, and you get that, which is 1 over n squared times the natural log of n minus 1. Now, what is y prime then? It's this times y. And so, for n bigger than or equal to 3, this is going to be positive. A positive derivative means an increasing function. And you're done. You've proven it's monotone increasing. Therefore, you know the lower bound occurs at the first term of the sequence. And we did this work up here to show you what the upper bound of the sequence was at 1. Okay? All right. Let's go down to some limit problems here to consider. And so we'll wrap up this section looking at these last few problems. Problem number 46. The author asks you, for a sub n equals the inverse tangent of n squared, what's the limit of that? And so see if that tells you whether this function generating a sequence converges or diverges. Well, the limit as n goes to infinity of the inverse tangent of n squared is actually quite simple to compute. As n goes to infinity, this is going to be the inverse tangent of infinity. And so all you have to realize is what the tangent function looks like. Okay, there's your graph of the tangent function. And so if you want to know what the inverse tangent of infinity is, well, infinity is up here, right? Going backwards through the tangent function, that brings you to pi over 2. And so that's your limit. Okay, let's try number 48. And that's kind of interesting, I think, in 46, that the way we actually compute the limit is by knowing what the tangent function looks like. Without knowing that what the tangent function looks like, this could be a problem that really could give you some difficulty to try to understand, I think. In 48, a sub n is the natural log of n squared over the natural log of 2n. And so I want to know what that limit is. The limit as n goes to infinity of the natural log of n squared over the natural log of 2n. And so the top goes to infinity, the bottom goes to infinity, and I say, okay, let's use L'Hopital's rule to work this. L'Hopital's rule would give us the limit of the derivative of the top. The derivative of n squared is the derivative of n squared over n squared. The derivative of the natural log of 2n is the derivative of 2n over 2n. And so when we simplify this, okay, the n's cancel here, 2's cancel here, and I've got an n and an n that cancel here, and so I'm left with a 2. Okay, the limit is 2. How about number 50? A sub n is the natural log of n plus 2 for n squared minus 3. So what's the limit of this? Well, you pass the limit inside the log, or think of it as pull the log outside the limit. And this limit here, infinity over infinity, you apply L'Hopital's rule to it. The derivative of n plus 2 is 1. The derivative of n squared minus 3 is 2n. And so you're getting the natural log of the limit of this, which is 0. And the natural log of 0 is minus infinity, so this diverges. It doesn't have a finite value associated with it. Okay. Final example I want to show you, number 52, is just how challenging it can be to work with factorials. We have 1000 to the n over n factorial. Okay? So think about what this looks like. In the top, it's 1000 times 1000 times 1000 over and over and over again, right? And in the bottom here, n factorial. So 1, 2, 3, 4, up to 1000, then 1001. 1002, and so on and so on and so on, right? Well, what's for sure here is that if you were to take these terms, the first 1000 terms, say, 1000 over 1000, 1000 over 999, 1000 over 998, and so on and so on and so on. That is just a finite value. We call it m. Okay? And then from then on, what you have is m times 1000 over 1001, 1000 over 1002, 1000 over 1003, and so on and so on and so forth. And so what is happening is these products that you're calculating are going to 0. And therefore the entire product of this is going to approach 0. In other words, the factorial is going to win the race over 1000 raised to the nth power. Factorial will grow faster than a power function and drive everything down to 0 in limit. Okay? All right, so that's it for section 5.1. I'm going to go ahead and get this video posted and do 5.2 separately. So good luck on your homework, and as always, let me know if you have any questions or concerns.